All right, hello, hello. How's it going, everyone? Say hello to the fish while everybody gets in here so I know I have an audience. If you're here, please say hi. How's it going? Oh, good one. Yeah, happy spring break. Ouch. It's unfortunate. How you guys doing? Did you have a good Easter? Happy Easter, everyone. I had a pretty good one. As you can see from the background here, we finally got some books up in the bookcase over there. Had my in-laws in town actually, and they wanted to help us continue setting up our house. Okay. So I hope you all had a good weekend. We're going to pick up where we left off last week with activated sludge and really the dynamics of growing bacteria for the sake of consuming waste products in the water. So wastewater treatment by using bacteria, growing bacteria, and we have this problem from the book. It's example 6.9. And essentially we have this pond and we want to know how much bacteria is in the pond when it leaves, how much substrate is in the pond when it leaves, and the overall efficiency that will derive from that substrate. So last time we introduced the problem and talked about it a little bit, and I mentioned that the approach is going to be a little bit counterintuitive. So hopefully you had a chance to take a look at this. If not, feel free to pause now or come back to this later to try before we solve it together. So the question asks, and this is where we're going to pick up, is do this problem, and then after we do this problem, we'll take a look at the case where we have recycling of those bacteria to improve the influent concentration so that it's no longer zero. So this X naught right now is zero. We just have some in the pond and they grow, and so to enhance that, we could recycle. That's going to be the topic for after we work this problem. So this problem itself can be considered as a typical CSTR, and we can solve it using the typical mass balances that we would normally use, with the caveat that it ends up making more sense to solve a mass balance for the X, for the bacteria concentration, in order to know something about S. And that has to do with the fact that our X, first of all, these two are interrelated, and the fact that X initial is zero. So for part A, that's how we will begin. So we can say our mass balance at steady state is equal to Qx naught minus what's leaving, Qx, plus the net growth rate. So now we have here we'll say R prime of G, and then we can fill that in a little bit more in a moment. I'm going to keep the book a little handy to use as a reference. And that R prime of G, well, let's go ahead and take the next step here. So X, or 0 equals, well, this X naught is 0, so that's going to be 0 minus Qx plus, this R prime of G is going to be growth minus decay, right? So our growth equation is essentially mu times X in that volume, and then we'll have a minus the death, which is going to be minus K dx in that volume. So that's going to be our overall term there. one thing we can do is we know something about mu. We learned last time that mu is equal to the mu max times s. This is just the rate constant for growth divided by ks plus s, where ks is the amount of substrate where the bacteria are halfway to the maximum growth speed. And mu max is the maximum growth speed. Okay, so then we can insert these parameters into the mu here so that we can get the mu in terms of s. That gives us a way to manipulate or understand something about the substrate, because what we're trying to do is solve for s. The other thing that we are looking for to happen in this particular problem is for us to get rid of x, because x is unknown and we need to solve for that later. So what you'll see is when we simplify a little bit further, every term has an x in it. So we can divide everything by x, and we can also divide everything by the volume if we wanted to get theta and to get rid of these guys. If we divide everything by q, that gives us 1 here, and v over q is theta. So let's do that. So this will be negative theta, because we're going to divide everything by v. We divided everything by x also, so that's just going to be negative theta, plus the x goes away, the v turns into a theta, v goes away because we divide everything by v. I just said that completely backwards. I'm sorry. I apparently can't talk today. So v over q is theta. So q over q times x over x is 1. So this is negative 1 plus mu. I'm going to substitute that in a moment. V over q is theta. And x divided by x is 1. So this will be theta times mu, which is mu max s divided by ks plus s. All that minus theta, because we divided everything by q, times kd, and x goes away. So this is our simplified version of this portion after dividing by q and x. Okay. So hopefully that makes sense now that I've spelled it out a little more clearly. From here, it's really just a matter of arranging the equation so that we can solve for s. So what I'm going to do is I'll go ahead and separate terms so that we have the mu max, essentially this term by itself and the other terms on the other side. So I'll go ahead and say theta times mu max s divided by ks plus s equals minus, so really I would have added these two to the other side. So this is 1 plus theta kd. And so all I did was I added theta kd and 1 to both sides and then just swapped positions. Okay, with that, we can now divide everything by theta and have mu max s divided by ks plus s equals, and dividing everything by that theta, we get 1 over theta plus kd. Of course, we could probably write that in a different way, which could still make sense. Then we need to get s by itself. So from there, we would multiply both sides by ks plus s, and then ultimately continue to simplify until we have s on its own. So mu max S equals Ks plus S times 1 over theta plus Kd. Then we'll need to factor those out, or multiply them out rather. So we have mu max S equals Ks over theta plus S over theta plus Ks times Kd plus SKd. Okay, so from there, we'll end up eventually dividing everything by mu max. We'll have the S over theta plus S times Kd. We can extract the S out of those two. And at the end of the day, if we simplify, we should end up, when we solve for S, and I'm skipping some steps here, what we should be able to get, if I've done that part correctly, is Ks times 1 plus theta Kd divided by theta times mu max minus 1 minus theta Kd. So that's our final equation, having started from here, doing a bunch of algebra to simplify, and ultimately finding S. Now, this equation works for any case where we have a CSTR with no recycle and 0 input of bacteria. So this is specific, and I'll probably give this to you as an equation, but you need to remember that it is specific to those exact conditions. To mass balance on X when CSTR with X naught equals 0, no recycle. Okay, so we can use that, and that's what the book derives, to find our value for S. If we needed to find S in a system with recycle, we're going to have different equations involved. So let me go ahead and open up Excel, and we'll put in these numbers here. And then we will get our answer. Okay. Let's see. We'll do this. All right, so we're going to need Ks. And I forgot to remind us here, but we had default values from last time. And so there's a few default values from the book that we were, in this example problem, we were told to use. So we actually have several values given to us in the book, and we had it last time, but I'll go ahead and just show you the sheet here. I'll do it on this one. This table gives us default values that we can use for this problem. I should probably not use that webcam for that, because that's my microphone. I apologize if that was really loud. Okay, so with those default values, we have a Ks default 60, and that's milligrams BUD per liter. Let's say K is 5 milligrams BUD 5 per milligram VSS per day. We don't need that one just yet, but we will. The mu max equals, as a default, 3 per day. The yield coefficient was 0.6. Yes, and in fact, it should already be posted to Moodle in the form of our slides from last time. So let me pull these up to show you. So if I have not posted these yet, I will, but this is the table here, 6.7. That's the table I'm referring to. Okay, so the yield coefficient then, that was milligrams VSS per milligrams BOD. And lastly, KD was 0.06 per day. Okay, so we've got those parameters, and we want to find our S for this problem. That's going to be equal to Ks times 1 plus theta times Kd. So we need theta. We have not calculated that yet, so I'm going to go ahead and do that first. This is V over Q. We want it in days because our other parameters are in days. So we'll say theta is the volume, 200 divided by the flow rate, which was, so that's 200 cubic meters divided by 50 cubic meters per day, cubic meters for both, and in days, so that works out great. Okay, so we have that now. I think that's all we need. Okay, so S then would equal Ks times our 1 plus theta times Kd, all that divided by theta times mu max minus 1 minus theta times Kd. And our S should be in milligrams BOD per liter. And if we double check in the book, that is the answer. So good. All right, so that means that we started with an initial concentration of 0.95 milligrams per liter BOD, and we ended with 6.9. So I'm going to move this aside for just a moment. Come back here. Turns out that S here equals 6.9 milligrams of BOD per liter. Okay, that's our answer for part A. And for part B, it's quite simple. B is just going to be the efficiency, which is essentially our initial minus what we ended with divided by what we started with times 100%. So that'll be, I'm so sorry. Yeah. Bye-bye. Thank you. I'm looking over here and not seeing the thing. I appreciate that. And the text will go away in a moment as well. Okay, so our efficiency equation then is simply going to be 95 minus 6.9 divided by 95 times 100%. And just looking at it, 95 is pretty close to 100, so it's going to be slightly more than 6.9% efficient. And we'll just do that on a calculator real quick. So 95 minus 6.9 divided by 95, so 92.7%. There we go. So that's part A and part B. And as you see, part A was a bit complex. It required a few algebra tricks with the mass balance. So that is fairly involved, but it's not really anything more than you've done before in the sense of we're adding rates into an equation, into a mass balance equation, and solving for some parameter based on what we know about those rates. Part C is going to be similar to that, and we'll need to derive a new mass balance. This time we do know something about S. That's 6.9 milligrams BOD per liter. And so now we can solve a mass balance on S to find X. So last time we did a mass balance on X to find S. This time we're doing S to find X. Again, it's counterintuitive, but we can do it because they relate to each other, and we were able to cancel out the X in the last equation. If we can't do that in a different system, we do need a different way to estimate this relationship given what we know. Okay, so this time we will say that we have 0 equals Q times S naught, that's our initial substrate concentration, minus what's going out, plus our, essentially our substrate utilization rate. So the reaction by which the substrate is leaving. So this is going to be QS plus a term that is our substrate utilization rate, which is V, should be, V times RSU. So the rate of substrate utilization. And we have, from last time, we had a relationship with the V of substrate utilization rate in terms of X, right? So we know that R sub SU, substrate utilization, we can write that as the kind of basically the inverse of the rate of growth. So rate of growth divided by Y, this uppercase Y. And so we can write that as negative K, which is that's the lowercase k, the specific substrate thing, times X times mu. So Kx times that mu, which we looked at last time, which is has to do with the, let me back up one step because I think it will be better if I make this a little more clear. So the rate of growth, R of G, is equal to mu x, right? That's equal to, if we take the mu and have it separate, that's going to be x times mu max times S divided by Ks plus S. Okay, so that's what our R of G is. Y, this uppercase Y, is equal to, or is related to mu max and this lowercase k. So Y then is equal to mu max divided by little k. So we learned both of those equations last time. You'll have both of these equations on your exam. So with that, if we divide this guy, R of G, by Y, then we'll see that the mu max is removed and we'll be left with a k on top. So we can write this R sub SU as negative k, because that k is going to come to the top. So we're dividing by mu max over k, times x times s. So that's simply the x here, the s here, and the k that's coming on top, all going to right there. Then we divide by the Ks plus S. So that should give us a term for the rate of substrate utilization. So that's going to go into it, and we'll say 0 equals, and we'll go ahead and divide everything by Q. So it's S naught minus S plus V over Q is theta times this guy. So that'll be times a negative Kx times substrate divided by Ks plus S. So what you see here is a term where we have X and some parameters, some of which we already know, well, all of which we already know, and we just simply need to solve for X. So you could just go ahead and put in all the numbers, and the only numbers left will be X, the only variable. Or you could go ahead and simplify this algebraically. And so I'll take a couple steps, and then there is a negative there because I was bringing the negative from right here. So when we multiplied the V times R of substrate utilization, that negative that's within the substrate utilization needed to come in. So I could have said theta times negative that stuff, but I just put it in front. Okay. So with that, what we can do is go ahead and move this to the other side. Get X by itself. We'll have theta, I'm just going to add it to both sides, theta X, theta Kx S divided by Ks plus S equals S naught minus S. From here, just looking at getting X by itself, we can say theta Kx S equals S naught minus S times theta Kx S, and then we would just need to divide by S, theta, and K. If I've done that right. This can simplify a bit, and we can say that that's going to be, you know, I did something wrong here. I'm missing the Ks plus S. I just didn't write it at all. That should have been right here. Yep. Okay, sorry. I was wondering that. It was looking pretty strange. Okay, there we go. And from here, and this X should not be there. There we go. So that is our simplification. Okay. So given that, we now have a term for X. This one was a bit simpler algebraically, but I still somehow managed to mess up a little bit. So we can solve for X, and when we do so, we use our parameters that we have, and it turns out that that X will equal 43 milligrams VSS per liter. Now, if you're unsure if you did your algebra right for this problem, then what you would want to do is take a look at the units and make sure that these units, you know, the units that you derived based on your algebra actually do match what X should be. So you know X should be, the problem even tells you, in milligrams per liter of VSS. And so a good thing to do to check would be to say, okay, Well, what are my units on top here? This is S, that's milligrams BOD per liter, times up here it's more milligrams BOD per liter. Okay, so milligrams BOD on the top. And then on the bottom here we have theta, which is in days, times S, which is milligrams BOD per liter. So that'll cancel. Times whatever K is. And then we have to remember what K is. And K, if we were to go back and take a look at our table, or even our Excel sheet, K is in milligrams BOD per milligrams VSS per day. So that's going to be milligrams BOD per milligrams VSS per day. And excuse me, I realize I just messed something. Here it's milligrams BOD per liter times milligrams BOD per liter. So that'll be squared there. So these will cancel with these two, at least the milligrams per, so the milligrams BOD will cancel all the way, the milligrams per liter will cancel once, so we're going to be left with per liter up here. Divide that by day, but then, so the days will cancel. Then what we'll be left with is per VSS, per milligram VSS on the bottom, which will come up to the top, and then we will end up with milligrams VSS per liter. So it checks out. So definitely encourage you to do the rate analysis like that, especially if you are in doubt. Okay, so there's our answer to part B. Any questions or issues with that? Okay, so my expectation for you is to understand that these equations that we derived are specific to this case where we have a pond-like system, no recycle, CSTR, bacteria growing, consuming substrate, with 0 incoming bacteria. I expect that you should be able to work with a system where X naught was greater than 0, or something like that, where the parameters are going to be different, and then you know that you can't use this, but you have to derive something for yourself. So I expect you to be able to at least approach the derivation for a new system, if not carry it out and solve problems with it. I will try to make sure that I don't overburden you with derivations during an exam, but I do expect you capable of doing that type of stuff. And again, that's for a system where this stuff does not exist, the recycle does not exist, and the X naught is 0. That's what we were just working on. So today, for the rest of the lecture, we're going to work on a system where we do have a clarifier. We are going to assume this works perfectly. We'll go over some assumptions in a moment. And then we recycle some of that waste to make sure that our X naught is high. And we want the X naught to be higher in a real treatment system because that allows us to be using all of the microbes' potential. If we have lots of microbes and they're all growing and eating, then we will consume waste faster or to a greater extent. So the control volume for this analysis that we will do is on this dashed line, but we will have some assumptions, like the assumption that no biological activity is happening in a meaningful manner, in a meaningful extent in the clarifier or the lines. Likewise, we will typically assume that our clarifier works perfectly. So this should be 0, XE should be 0 if perfect clarifier, if we make that assumption. Okay, and I think I've got a slide that kind of details this, yeah. So our assumptions, perfect clarifier means that XE is 0. That is very helpful because then our mass balance on the microbes is that they all go down the waste line. Well, then they split between the recycle and the waste, right? They split in either direction based on, whatever amount, whatever we are wasting is not going to the recycle, or on the flip side, whatever we're recycling is not going on the waste. But we can know the concentration based on the flow rate here and the amount of X we have here, because all of the bacteria are going that way. It simplifies a lot of our calculations. Okay, and the fact that there's no biological activity in here means that we can use the volume of our aeration tank as the primarily important component. And again, it's actually a decent assumption because we're not supplying the clarifier with extra oxygen. Water is just going to pass through that rather quickly, not, at least not for long periods of time. And we definitely don't want to be bubbling air into it because we're trying to clarify the stuff. Okay, the other thing we know is that the XR here is equal to the XW, because this is just simply a pipe that splits into two ways. There's nothing that would change the concentration, right? So XR equals XW. And the other thing we know is because XE is 0, so that's 0, because it's a perfect clarifier, then we know that the XW, this amount that's wasted, coming down here, is going to be at a higher concentration than X in the tank. And that's guaranteed because, so long as we have any flow coming down through the clarifier. If we had no flow coming through the clarifier, if it was 0, if we have any flow coming out the clarifier this direction, essentially that means that we are concentrating this. If we had no flow coming off the top of the clarifier and it's all just going to waste, then it's just the same concentration. We have not done anything to concentrate that water. In this case, we are sending lots of water that's presumably clean, at least of the bacteria. We're sending it out that way, so then we have kind of nothing coming in here. Okay, so those are our assumptions, and those are the tools that are essentially going to simplify our calculations. The other thing to note here is that this really highlights the reason it can be very bad if you have a situation where your sludge starts bulking and floating. So when you have sludge flotation in your clarifier, it really messes with this math and these assumptions. And so treatment plant operators will try very hard to keep the sludge in a suitable state. If you grow the wrong type of bacteria, maybe your pH changes a lot and kills off some bacteria and the wrong stuff starts growing. Maybe you have too much fats and lipids from restaurant grease coming in and providing the right kind of nutrients for the wrong type of bacteria. You might get a situation where you have bacteria growing that produce lots of filamentous stuff, and especially with all the bubbles that are added during the aeration, you get floating junk. And this floating stuff, it just excessively, there's an excessive amount that floats, and it all or a lot of it goes out the effluent, and that's bad for several reasons. First of all, you don't want that much bacteria leaving your wastewater treatment plant, or leaving your effluent here to treat with disinfection or whatever. But also, it's going to reduce the amount you can recycle, and thereby reducing the amount you're going to have at the start, and therefore reducing the effectiveness of your aeration tank. So it's an error that has lots of feedback into the system to really which causes a lot of problems for your wastewater treatment. Okay, so there's a couple of concepts here that are important. And the first, and this is also an equation that I'm going to give you, is the food to mass ratio. Now, when I say food to mass ratio and we write it as F to M, we are using F to M. This is one variable that you should never separate food versus mass. You should always keep it F/M. So we'll say one variable here. So for our purposes, do not separate them unless you're separating them with this stuff, right? So do not multiply both sides by M. That's not going to have a meaning. Rather, manipulate on this side of the equation if you're going to do anything. Okay, so just keep that as the one variable, even though it looks like it's one divided by another. What it means is the amount of food available to microbes compared to the amount of microbes there are, in terms of the mass of microbes that exist. So the way we can describe that mathematically is, and it's actually not just that. It's not just the ratio, but it's the ratio over time. So given it's the amount of food supply on an hourly or daily basis or whatever, the food supply per mass of microbes. So if you think about it, if you want to feed a small party at a picnic, you have to consider how many people there are, and you might even want to consider how large the people are. If you're feeding a team of football players, that's going to be different than feeding a group of very tiny individuals, or people with small appetites or whatever the case. So you might want to think about that kind of dynamic. That's what we're looking at here for the food to mass ratio, except we're dealing with microbes. So you have flow rate times the substrate concentration. That's your food. And that's actually the food per time, because that's going to be, a flow rate is volume per time multiplied by the substrate concentration that's coming in, that S naught, it's coming into the equation. That's going to be mass of food per time, per volume. So we'll just say M per volume there. So these volumes will cancel. That's a mass per time unit divided by V times X. So this is, first of all, this is mass of food per time coming in. And that looks very much like our typical mass balance, a mass per time, it's a rate. And on the denominator then, V times X, this is going to give us the mass of microbes. So volume is obvious, times mass of microbes divided by the volume that we're dealing with for that concentration. So the volumes again will cancel. So then we're left with this mass per time per mass. So it's mass of food per mass of microbes per time. So just like what you think it is, it's the amount of food per the amount of bacteria per time. So very simple when you think about it, but the way we write it out mathematically would be QS naught divided by VX. Okay, so that's the food to mass ratio. This ratio is very important because it determines what type of microbes can thrive and reproduce. There are some microbes that actually require in order to compete with other microbes, that they do really well if there's food sometimes and not other times, for example. Some microbes will really do the best and be able to outcompete everything else when there's a constant supply of food. So you might consider that you, in operating your treatment plant, you want to make sure you're monitoring the amount of microbial food that's coming in and adjust your parameters based on how much food there's going to be. And the thing you can manipulate is actually the mass. So depending on what strength your wastewater is, you can potentially change how much mass you're wasting in the waste activated sludge line, because if you increase that, then you're decreasing the recycle. So if you increase the flow this way, you have a smaller flow here, whereas if you shrink the flow through the waste, then you're going to have a larger flow going this way, because it's going to have to account for the same volume, same flow rate either way. So it turns out that this QW controls a lot of the important parameters in the system. In fact, I would call that probably the most important design parameter or control parameter for the activated sludge system with recycle. Okay, so you want, I mentioned the sludge flotation earlier. So one of the things to keep in mind is you want a consistent food type and a good range of food to mass ratio to keep the right bacteria happy and growing and outcompeting any other types. We can typically assume that the wastewater treatment system is going to find all sorts of different types of microbes. You're going to have a large variety of microbes that exist in the system, but then only a few species are going to outcompete everything else. So there's only going to be a set number of bacteria, maybe 4 or 5 species, that occupy the 95% of the mass of microbes. There's going to be lots of others, but what we want is to keep the good ones, the ones that are doing most of the work and are also not causing flotation. We want those to continue to dominate, or if something bad happened and we do have flotation, then we want to perhaps adjust things to allow the right type of microbes to recover and become the dominant population again. Okay. So there's a couple things to consider when we think about our hydraulic retention time. So when we recycle, and this is a kind of an interesting concept here. When we recycle water, you might think to yourself, well, we're changing the amount of residence time that the water spends inside that tank. That you would be right to think that, except that we've drawn our control boundary out here outside of the recycle. And we've assumed that there's no biological activity in the clarifier. So what that means is there's some volume where aeration and biological activity is happening, and there's some net flow coming into the control volume, and that same amount going out of the control volume. So if we look at the Q, that Q is going to equal QE plus QW. Nowhere in that mass balance or in the balance of flows does the QR show up if we're dealing with the mass balance with using that control volume, because we always deal with what's at the boundary of the control volume in order to understand the system. So even though we actually have a higher flow coming in here and leaving, we are also recycling that. And so the net effect is nothing in terms of the hydraulic retention time. The hydraulic retention time does not change at all. And that has to do with the way we've defined our system. Now, One thing that will change is the solids retention time, which is a new concept that we need to discuss. Okay, so hopefully that makes sense about the flow rate going in and out. There's no other volumes that are important. It's just this guy. And you would think that this would be our control volume, but because we made that no biological activity here assumption, then we can do it across a wider range of the system. So then, solids retention time, and here it looks like a waste-activated sludge line pouring into a tank here. The solids retention time is tracking how long that the microbial solids stay in the system. So we're going to call this the cell retention time or the solids retention time. And what we're going to follow the book's example here and say that this is theta sub c. So theta c for cell retention time. Our solids are in the form of bacterial cells, which is why we call it that. Okay, so our solids retention time is going to change based on the recycle. So we need an equation to understand this, and it's not going to be the same as the hydraulic retention time if we have recycle. If we did not have any recycle, it would be just the same because it's a V over Q system. So our theta C then, we want to know the mass of solids. We ultimately want to end up with an amount of time that they spend there, right? So we're looking at the solids, and essentially what we're going to do is take the mass on top. So that's Vx. That's going to give us volume times mass over volume. So that's going to be just mass divided by, and on the bottom what we want is a mass per time, so that we divide the masses, those cancel, and we're left with time on top. So down here we need the flow rate times x, and what we're looking at is the amount of time in the reactor divided by the terms leaving the reactor. So we've got Q times X on the bottom and Q times X again. So the units on the bottom are going to be the flow rate is volume per time, and multiply that by our mass per volume. Sure enough, the volumes are going to cancel. We're going to have mass on the bottom and per time on the bottom. And so ultimately that gives us time, which is what we want for a solids retention time. Now, this is accounting for essentially the mass that exists within the reactor divided by essentially the rate at which mass is leaving the reactor. So we're looking at X inside the reactor, and we're dividing that by the flow in which it's leaving. Okay? So one thing you'll note here is that if we have a perfect clarifier, we said that this should be 0. And so our solids retention time becomes simply Vx divided by Qw xw. So then this tells us something about if we increase the amount we recycle. I told you a few minutes ago that that means we have to decrease the Qw. So Qw is essentially controlling how much we recycle, which is controlling how much time the mass of microbes spend in the reactor. And this cell retention time is another parameter that affects that food to mass ratio. It plays a direct role there because it controls, in some sense, how much microbial mass is in the system. Okay, so let's take a look at an example problem with that type of system in mind and compare it to what we were dealing with at the beginning of class. So let's take a minute. I'll read this to you, and then we will work towards this. Actually, let me take a quick look at what else we've got here. I think just a few. Yeah. Okay. So this example problem says, consider a wastewater treatment plant that is being renovated to include a return activated sludge, or RAS, line. Assume the influent MLVSS, so mixed liquor, volatile suspended solids, that just means the microbe concentration, is 0 when you have no recycle line. The following parameters are known about the reactor, which acts as a CSTR. So it gives a bunch of parameters that we might need. Some of them are going to be similar to those default parameters we have that table for we looked at a few minutes ago. Part A says draw a schematic of an activated sludge system before and after the recycle line. So activated sludge before, we have, and I'll let you go ahead and take a moment to sketch this out on your own. So think about that. Look at the fish back here. Okay, so when we consider an activated sludge system with no recycle, and this is within the context of some sort of wastewater treatment, then we probably have some sort of primary effluent. So what's leaving the primary effluent is entering here. You know, this might be a clarifier or whatever. Then we have activated sludge, and then the next step would very likely be another clarifier to capture those bacteria and go about its business. So very simple, activated sludge is here, and within the secondary treatment, we'd probably have a clarifier following that. We'll talk about another time how we can actually use membranes instead of a clarifier, and that's called a membrane bioreactor. Okay, so after adding a recycle line, then we'll have that primary effluent coming in, and again we'll have a clarifier coming out, and this time we're going to go ahead and recycle some of that. So very simply, just asking you to draw essentially what we were looking at a moment ago, and hopefully recognize that within the context of a wastewater treatment plant, the clarifier is very likely going to be there. Okay, part B then asks, what is the final substrate concentration in the no recycle system before the RAS line is added? We've got all these parameters here. So really this is asking the same question we looked at in the example problem at the beginning. So what is the final substrate concentration in the no recycle system that's just like the pond? So what we're looking at is we have our waste activated sludge, probably some clarifier, and what we're wanting to know is the final substrate concentration here. We know something about the initial concentration, that the concentration of the primary effluent is 220. And so that's what it's asking for, is the substrate, the final substrate. So I'm going to leave this to you to solve on your own if you want that practice. So this is going to be essentially the same process that we did at the beginning of class, and it'll be good practice for you to make sure that you understand how to apply that equation. Maybe it would be good to practice deriving that equation based on the assumptions and prove to yourself that you can work with this system, and you can take a look at the two different reactions that are going on, the rate of growth and the rate of death, and how those play a role together in that mass balance. So here we would do a mass balance on X first. Part B, C, asks what is the BOD removal efficiency? Again, on your own, this is kind of the same deal. And part D is also asking what is X final. And again, I'm going to say on your own based on what we looked at the beginning of class. And so this parts B, C, and D are basically the same as example 6.9 that we looked at, just different parameters. There's also some different language, by the way. So in this case, I said the substrate concentration of the primary effluent. So another reason why I wanted you to label, and I spent some time labeling that, is so that you know what primary effluent means. That's common language used for this type of problem. And you should be able to see that what that's referring to is the stuff that's entering your secondary treatment step. Okay, part E is where we start getting to a different problem. So part E says if the sludge produced has a concentration of 12,500 milligrams VSS per liter, which is now recycled via the new recycle line at a flow of 150 cubic meters per day, what is the resultant influent, in quotes, MLVSS concentration in milligrams per liter entering the aeration tank? And then I give a hint to refer to your initial drawing. So we'll go ahead and draw that again. Okay, so I'm going to let you think about that for a moment, give you a chance to consider this, and I'm going to step away for a moment, use the restroom, and I'll be back. So take this moment to come up with an answer to this problem and think about how you would approach it. So I'll be right back. All right. Okay, so hopefully you had a moment to think about that. And what I will say here is, in my experience, students often overthink this problem. And you, especially if you're kind of considering the different equations we might have just learned and trying to figure out how to apply them here, this problem, you actually don't need any of them yet. And the reason for that is it's just a very simple mass balance right here. So we know we have a flow rate. This is the flow rate of the plant essentially. And we have X naught was given to us as 0. And then we have XR and QR. And the question is asking, what is the new, quote, influent MLVSS to this reactor, which is right here. This is what's coming in. So we'll say X naught prime. That's the question. So if you refer to your drawing, then you should be able to see that really what we need to know is just that. X naught prime equals, and when you take a look, you can say that, okay, well, this is just a simple balance of two streams meeting. We've done this since basically day 1 of the class. And we can say Q X naught plus QR XR. These are the two things coming into this little control volume I drew, is going to be equal to what's coming out, which is the Q plus QR. So that's the total flow rate in this line times the X naught prime. So with that, we can say that Q X naught is 0. So 0 equals QR, or excuse me, 0 plus QR XR equals this Q plus QR times X naught prime. And so then we can solve X naught prime equals QR XR divided by Q plus QR. Okay, so then we just need to make sure that we have those terms. We know that XR was given as 12,500 milligrams VSS per liter. Q was 0.01 cubic meters per second. QR was given to us in day units, QR, so it was recycled as 150 cubic meters per day. So we'll need to convert that to seconds, but otherwise that's really all we need. So let's get that Excel sheet going again. And that will get us to our solution here. So we'll put in our parameters. We're going to take that 150 cubic meters per day and divide it by the amount of seconds in one day, which happens to be 86,400. That will get us into cubic meters per second. So we can solve for what we're asking for and say this is going to be equal to QR times the XR divided by QR plus Q. And so, as we might expect, our answer is smaller than the recycle concentration. We have a large volume of, I guess a large flow of water coming in with nothing. We're adding a highly concentrated but small small flow rate stream here, and so the combination should be something that is definitely above zero, but also definitely below the recycle concentration. So that's going to give us a final x naught prime of, what was it, 213 milligrams VSS per liter. Okay. Any issues there? If not, the next part of this problem says, in the new system with the recycle line, the resulting food to mass ratio is 0.58 milligrams BOD per milligram VSS per day. What is the new mixed liquor volatile suspended solids concentration in milligrams per liter VSS? So what we're looking for is a new X concentration in the system. Now, remember that our food to mass ratio, this was going to be, was it QX, VX, right? VX divided by QW XW. Let me just double check that we've got that right. VX divided by QW, oh no, that's solids retention time, I'm sorry. Right, we're looking at the mass of the food, right? That should have been obvious. QS naught divided by VX. Okay, that's the proper one. So our food to mass ratio, the amount of food versus the amount of mass in per time, in a per time situation. So we are given the food to mass ratio. We know this is equal to 0.58 milligrams BOD per milligrams VSS per day. So we know that, and we also know Q, we know the substrates that we start with, and we know the volume of the reactor. So really the only thing that's unknown here is X. So we can just simply solve that for X. X is going to be equal to Q S naught divided by V times the food to mass ratio. We can solve that. Again, we'll just go over to Excel and say, we have Q S naught equals 220. Our volume was 550 cubic meters, and the food to mass ratio is 0.58 milligrams BOD per milligrams VSS per day. So then, our new X is going to be equal to the Q times the S naught divided by V, also divided by the food to mass ratio. And I think this is wrong. I think I did something. Let me just write it out properly here. This number looks wrong to me. It should be a higher concentration, I would think. So I think, let's see. Let's check the units. Make sure we're following what we should have done and didn't need any conversions. So Q times S naught Oh yeah, what we're looking for is food to mass ratio in days. This was given in days here, but the flow rate's in seconds, and I forgot to convert that. So let's make sure we include that conversion. So the food to mass ratio here, let's take the flow rate in days. That's 0.1, and we're going to multiply it by the amount of seconds in a day. It's 86,400, or we can write it as 3,600 seconds in every hour times 24 hours. Okay, yeah, and that's just times 0.1, which is why we dropped a 0 there. Okay, so that's cubic meters per day. So instead here we need to use, instead of B3, we need D3. Okay, that looks more reasonable. That's a number that is certainly larger than the 200 that we got coming in a moment ago into the system. So here we have our X concentration at 59,058. Excuse me, 5,958 milligrams VSS per liter, just based on that food to mass ratio. So some of these equations are actually kind of nice, because if you have the equation, then and you're given some information, you don't even have to worry about the reaction that's going on if you already have this knowledge. So in some ways, dealing with the recycle line is actually somewhat simpler because we have some of these established relationships that we can work with. Okay, part G asks about the flow rate of the waste sludge line. So the QW, what is the flow rate? What is QW? Sorry, if this would let me, here we go. What is QW? And I tell you to go ahead and assume a value of 400 milligrams VSS per liter in place of that, whatever value you calculated before. So this essentially is going to use the equation we derived for QW. I'm going to go ahead and let you solve that on your own. We'll pick up here next time, and then I believe we'll start working on the looking at BOD, how to calculate BOD, how to determine BOD in an experiment, and what happens to BOD as you go downstream from rivers. I will begin working on grading your exams soon, probably before then. So perhaps we'll take Thursday and go over your recent exam together, even though I'm fairly certain I will not have them fully graded for you by Thursday. Hopefully sometime next week I'll have the grades for you. Okay, with that, that's all I have for you, and I will see you guys on Thursday. I'll hang around for a moment if there are any questions. All right, goodbye for now.